Let us come to the discussion. So what we have seen in the last lecture is the different dynamic characteristics, out of which we have seen a few important one, that is uh, the response time, the delay. Okay, so this thing we have seen, and the fidelity also we have seen. What is the meaning of fidelity and how it is. Am I audible to you all? Please let me know. Am I audible to you all? Yeah, right. So we have seen regarding fidelity is nothing but how faithfully we are represent the signal. Then we have seen the next part, that is dynamic error, which is nothing but a difference between the true value and the quantity that is changing with respect to time. So at any instance of time, what is the true input given and the one that is represented by the system under the dynamic characteristics, that is called as a dynamic error. So and we have discussed that it is very difficult to find out the dynamic error if we consider there are some static error. So the assumption in this criteria is that there is no static error present, or whatever static error is present, we already have removed that by having the calibration, right? So in this regard, the total dynamic error of the instrument is the combination of its fidelity. So it's very obvious to understand. I think we are about to discuss this in detail in the today's lecture. So as per this, coming to the graph, now this fidelity indicates how faithfully the signal is, the input is represented. Say for example here, at this particular input, the ideal input given to the measurement system is here, and this is what is represented as output. So there is a difference, and this difference may be in the form of the amplitude or maybe in the form of the delay, that is lag we say. So this also is going to take part into the dynamic error. So that is what is said, dynamic error, total dynamic error is the combination of the fidelity and the time lag. The time it takes to represent some output for given change the input, right? Or the phase difference, if the input is something of the form of the sinusoidal waveform, say this is the input, the standard input given, the output represented by the system will be something else. It will take some time to represent. If I show this with the dotted line, so it means that at this particular instance of time, the input is this, but the output displayed is this one. Whereas for the same input value, the output corresponds here at some time which is at different event, a different element, that is with the delay, right? So it is a combination of the fidelity and the time lag, or the phase difference between the input and the output of the system. Then we see the next important property is the overshoot. So again, if we consider a system, I think this will again come into due course of time, the example. Suppose we have applied some signal here. So this is the true input that I am going to apply. Now to this input, the response will be something slow response. It will take some time to reach. But sometimes we find that it gives some kind of rapid response by which it shows something higher value than what is given as the input, because of the initial excitation and the characteristics of the system, like it has got some inertia and something. We find that it is having the overshoot, and then slowly it comes to the settled value, right? So the reason behind this is the inertia is there. Say moving parts of the instrument have mass. There are definitely some components involving with the mass of the component, in the measurement system. And if suppose sudden motion is given, because of the motion, the mass starts accelerating. Then because of the acceleration, it picks up the speed, and many times it shows some output reading which is even greater than the value of the input given because of the initial excitation, right? So when an input is applied to the instrument, we find that the pointer or the instrument does not immediately come to the rest. The settled value, the true input, suppose is given here, this is the true input, it does not come to the settled value at once, but it shows something higher value, and then it goes on having some kind of the wave pattern, right? So it shows that before coming to the steady state or the final stage of what is the faithful representation of the input, the overshoot is observed, and that is the say definition of the overshoots. So the overshoot is nothing but something which is showing the highest possible value beyond the true value or the standard input value given to the system. So very first representation of the measurement instrument or measurement system is something higher than that of the standard input given, and then that we call it the overshoot. So this overshoot is evaluated as the maximum amount of the output by which the moving system. Anything to be discussed? Harshili, you want to say something? Your mic is on and it's welcome. You are welcome. You can ask the doubt if it is there.
No, sir. It was by mistake.
Okay, it's okay. So the overshoot is evaluated as the maximum amount of the output that is shown, for which the system having some component as say in motion or something, it beyond the steady state position. So steady state position is somewhere here. So whatever value that has been represented by the measurement system above the steady state position at very first instance of the measurement site, we call that as an overshoot. So in many instruments, most of the instruments we find, there are some elements which are going to have the initial excitation, and because of which there is overshoot seen, especially galvanometers. It is desirable to have little overshoot. It is desired because there is, we cannot say make it zero. So it is there, it is bound to be there. So many times it is even say accepted or desired also. But the excessive overshoot is undesirable because otherwise system will take long time to settle down. You can see the pattern. As the overshoot value is minimal, we find it gets a smaller time to show the steady response. The measurement will be more steadily observed, right? So now this is the diagram. We have already represented few part of that, but definitions are given here. Say for example, this is the input applied. Say for example, this is the standard input given, and the system responds to the wave in this format, and so on, right? So the overshoot is nothing but the distance that is shown here, the amount by which the output of the measurement system is exceeding the settled value or the true value of the input if it is known. So very first instance, whatever has been shown, this is nothing but overshoot, right? So in this one, we can have few more classifications of the diagram here. At certain point of time, it assumes more or less settled value. Say for example, it will now settle down afterwards. Now when the settlement of the reading shown are between plus or minus 2% of the band, then we say that this is onwards is the stable output shown by the measurement system, right? And the total time that has taken to take the settlement here is nothing but the 2% of the settling time, whereas a final steady state level that already we have shown in the form of standard input applied. Now there is some time taken to reach 10 to 90% of the rise time. So for example, this is the output shown corresponding to 90% of the input value given. Then in that condition, we consider one zone that is representing 10 to 90% of the input being shown as a the display at the instrument. So that is say considered as a definition or some term called as the rise time, which is for rising the output from 10 to 90% of the input supplied, right? And the maximum value at which overshoot is measured, that we call it as a peak value, peak level. So these are the definition that you can find in any of the standard text available. Any doubt in understanding overshoot? So what is desired? Smaller overshoot is desired. The reason is very clear. As the overshoot is larger, it will take longer time to settle down for the steady state output being represented for a given say standard input. But it forms a very important property, and based on this, many of the instruments or many of the measurement systems are say preferred, or the merit of the system is being preferred based on the overshoot quality. Then we'll try to see the next property. The input signals are required. And we have already said that the instrument, the measurement system, we are going to apply some kind of input and finding the response of the system. When that will be placed for actual measurement, we are not sure what kind of input it is going to have. But approximation of the actual input can be say understood by resembling it more closer to some input forms, the standard input forms, right? So the measurement system can be, that's what we are talking about, can be subjected to any type of input which we may not be aware in actual practice for measurement. So the only standard method or only known method for finding the dynamic characteristics of the system is to have some approximation toward the actual signals that can be applied to the system, and we then test and validate the system for the standard inputs. Okay. Since the applications in the signals and the are they are random in nature, and the type of the input signals cannot be known exactly. We cannot have any prior knowledge of how the input signal will be recognized as. So it becomes difficult to express the actual input signal that is applied to the measurement system. And because of this, we are not very sure how the system is going to perform, and what are the dynamic characteristics of the system will be very difficult to know. So the only method is for the study of the dynamic behavior of the system, we approximate the real input that can be applied to some standard formats of the input. So certain standard signals are employed, then the equivalent or say more approximated standard signals are then applied in the standard test condition, and then we calibrate or we note down the response of the measurement system to the dynamic behavior. Okay, so the of which mathematical equation can be developed. That is the major difficulty. Say for analyzing the dynamic response, we must know the nature and the mathematical representation of the input signal, which is very, very impossible in the practical case. But if we are approximating the real system signals to some standard approximated values, then we can easily formulate the mathematical equations, and thus the dynamic behavior can be studied. So this is something we are trying to bring more approximation towards the dynamic characteristics predictions, right? So the dynamic measurement is generally done in the static say signals, where the signals are applied as a steady state signals. Then the signals can be in the say dynamic nature, having the periodic type of the signal. So steady state periodic signals will be given, or that can be non-repetitive or transient signals, which are basically the single pulse or aperiodic type, or continuing or random type of the signals which are given. So the input is continuously changing, and the instrument gives the output signal continuously. Say as the input applied is going to change continuously, output also is going to change. So under such situation, we will not be able to have the dynamic characteristic clearly defined or clearly found out, right? Wherein the output depends on the nature of the input. So if the nature of the input signals are going to change, output is going to change continuously, right? So different types of the inputs are thus possible, which are approximating the real-time signals given to the measurement system. So now this dynamic measurement is carried out with the type of the signals. Say out of those, the standard signals are of step format, RAM format, sinusoidal format, and the impulse format. Other than the standard, those are in the wave pattern. So it can be square or sawtooth wave, and then it can be combination of the standard as well as the waveform. So there are multiple waves with the different frequencies and different amplitudes can be, say, designed and given to the measurement system, and dynamic behavior can be calibrated or found out. Or there can be modulated waves. And the last one is the random kind of the input signals. That is very difficult to formulate any kind of the equation or characteristics of the random input given as a to the measurement system. So this, though we are defining this, we have got different types of the input signals. Our study will be very limited because of, say, the standard signals which are very clearly known, of which mathematical formulation or mathematical equation is very clearly known, right? So only we can apply the very known standard signals or very regular signals like step, RAM, sinusoidal, impulse, and at the max the waveform, square, sawtooth, and other one. But in the real-time situation, we will not be able to consider the combinations because this goes on becoming more and more complex. Right? So random, it is highly difficult. We cannot give the random signal to the system and get the dynamic characteristics anticipated for those random signals. Right. Let us understand this now. The standard input signal are also called as a periodic signal because those are going to change with respect to time and it is going to repeat in the cycle. So it varies with the cycle. So after a certain period of time, it is going to repeat itself in the format. So repeating itself after a constant interval of time, and thus then we have got the response may be harmonic, having the same amplitude above and below the line symmetry, or it can be non-harmonic type. So here we have got the periodic or harmonic signal. You see here the input signal is varying in the form of a cycle, so time period is going to remain same. Right? I think you are all aware about this. You have gone through somewhere this kind of signal. So this is called a periodic harmonic signal. Then we have got periodic sawtooth type of the input signal, where again the time interval is the same. The input signals are going to vary and then it is going to be repeated number of times. Then there can be another waveform that is nothing but a square tooth waveform. Right? So the examples can be given. The vibration excitation due to the unbalance of the rotary mass, we find it is going to repeat as long as the speed of the rotary mass is going to remain steady or the more or less constant. We find that the excitation due to the unbalance of the rotary mass is going to be the harmonic input. Whereas the another example we can give is a pressure variation in the cylinder of your internal combustion engine. We find it is periodically changing. So here also some conditions are there. If the load conditions are going to remain more or less constant, we find the pressure variation, the pressure wave that is generated inside the IC engine cylinder is more or less going to exhibit the periodic nature of the signal. Whatever is the signal generated per given time will be repeated with same amplitude number of times. So these are the standard input called as the periodic input signals. It can be either harmonic or non-harmonic. Then we go to the transient input signal. The transient name itself suggests that it is varying, not as a cyclic variation. So probably the time period may be different or the amplitude can be different. So the signals are for definite duration. The time remains same, but amplitude is not fixed, right? So it becomes zero. It comes to the rest or comes to the zero level after the constant intervals. So example is nothing but a force due to the explosion. If there is an explosion in a confined boundary of a system, and if we are going to measure the pressure or the forces, in that condition we find those are called as a transient response. the transient input. So here you can see the given amplitude. The amplitude is changed with respect to time. It comes to 0 at certain interval of time. So signal ends there, right? So there can be, say, different waveform, a triangular or rectangular or so on. The rectangular waveform, triangular waveform, and so on will be called as a transient input signal. I think this is very clear and very simple to understand. You might have gone through somewhere else. There might be some kind of repetition even, right? Then we come to the random input. So name itself suggests is varying randomly with respect to time. So it has got no definite period, neither the amplitude. This may be continuous but maybe non-cyclic. So example is nothing but fluctuation into the near the in the pipe, say for the turbulent fluid flow. We call that as a random signal, and it is very clearly shown. The amplitude is not even repeated, and time is also not repeated. Now, I think I have made it very clear that we cannot apply the random signal, or we do not apply the random signal because it's very impossible to replicate. So you have to understand the process of calibration in case of the static characteristics as well as dynamic characteristics is more or less of the same method. The method is going to remain same. We have to apply the standard input number of times and then take the readings. That's what we have done in case of the static characteristics. So the same input that is maybe varying with respect to time, the same cycle or same set of the input we should be in a position to apply, which is not possible in case of random. The name itself suggests. If it's not possible to apply, then we will not be able to have the mathematical formulation or the representation of that in terms of some kind of say mathematical entity, and thus it is very difficult to find the dynamic response for the random inputs. Right now, under this kind of inputs, we should have a standard approach of finding the dynamic characteristics of the system. See, this approach is nothing but we are going to represent first of all the measurement system in the form of mathematical model. We must know what is the input-output relationship between the particular component, maybe physical component or the say functional component of the measurement system. So we must represent, or this is a very standard method to represent the measurement system through a mathematical model. Then to this mathematical model, we supply some kind of input signals in the form of the mathematical formulation. We then are going to have the formulation which governs the relationship between the dynamic input and the dynamic output signal of the system, and then we obtain the dynamic output response for the given input by solving the governing equation. This is a standard method or approach for finding the dynamic characteristics of the system. Then what if the response of the system is not as per the desired? Say, now I'll give the example here. The system, suppose we are designing for measurement of the pressure under dynamic condition, and we know that maximum pressure that system can have. Say for example, again the IC engine chamber, the maximum pressure that can be generated is anticipated by our governing equation of the phenomena. Then we know that in the given fraction of time, say small fraction of time, we are going to have large variation in the pressure, and we want to say capture those. So the boundary limits within which measurement instrument have to perform is known. If suppose we are applying and we find that the system is not giving the proper response, we will attempt for improvement by the method of compensation. Though it is very simply written here, and actually it is very difficult for the compensation in the dynamic condition measurements. In static condition, it was very simple. Say for example, I'll take again the example of vernier caliper. If I know that vernier caliper is going to have a plus 0.01 mm as a readout, so I can compensate whatever reading that has shown. I can subtract the same amount of reading, and I can get compensation. I can arrive to the standard value of the input. So similar attempts are done into the dynamic characteristics, which are a little complex than the static conditions, but it's a standard method that the compensation is applied. Right? Any doubt in understanding this? Then I think we'll. Who is Rishikesh? Rishikesh, you can respond. Rishikesh, what is the roll number, Rishikesh? What is the roll number? You can say give the response to me. You can have the audio on. What is the roll number, Rishikesh? Why you are not joined with the roll number? You please join with roll number. I will not allow you to enter any time without roll number. Nobody will be allowed to enter into the class without roll number. Anybody else is there who is entering into class without roll number? It's very simple question from my side. If your roll number is not known, how we should count you for the attendance? So I think this is not to be repeated. I should not find anybody entering into class without roll number onwards. So now we are going to understand the mathematical formulation for the measurement system. Say in general way, the measurement system that he's saying Webex changed. Okay, leave it. The generalized mathematical model of the system must be, say, formulated, and then the equation can be given as a linear equation for the time variant measurement system can be given as, we say, all the output parameter on one side and the input parameter on the other side. So these differential equations with the constant coefficient will represent better way the response of the system. Now to understand this, again you can come to the block. Say, let us assume that this is nothing but your measurement system, and to this there is some input signal which is represented as the output by the display by the measurement system. So this equation corresponds to the response of the measurement system to the given input to represent the output of the system. Qi is the measured entity that already I have said. Qi is the input quantity, Q is the output quantity, and the constants A and B are the combination of the physical parameters. So once we are going to form the linear differential equation with a constant coefficient, we will be able to represent the system in the form of mathematical model. That's what our first step. We are going to represent the measurement system in the form of mathematical model. Then we are going to either apply the normal method or classical method for D operator, or one can go for the Laplace transform to get the solution for these equations. Now, in this condition, the output of the system is to be found out. Now let's assume that we are going to apply the different input here, say Qi, though I have given here as the input. We cannot have the different values of the inputs given. So normally we assume, or it is, say, even practically very tedious and difficult to get the various formats of the input supplied, because as per our calibration method, if we apply more than one input at a time, we will not be able to understand to which input the output is faithfully representing, or where the output is given, for which input the output has been shown. So it is always required, or it is always desired, that we should apply a single input at a time, so that some dynamic or some static characteristics of the instrument can be found out as per the calibrating process. So here we are restricting ourselves to very standard input, whereas the output parameter can be numbers, the different values here. So that depends on the type of the response the system gives, and based on the mathematical equation of the system. So now method of D operator is the differential operator in the form of d by dt, and then we can represent the same equation in the form of an dn plus an minus 1 dn minus 1 plus a1 d1 plus a0 times output is equals to the constant b bm dm plus the output quantity in terms of the constant bo times the input in terms of the constant bo into qi. Now on solving this, we will be getting the total solution, which is consisting of the complementary function and the particular integral of this linear equation, right? So QCOF will be indicating the complementary function, which indicates the variable response, that is a transient response of the measurement system, and then the QOPI, that is the particular integral of the solution part, will be giving the response after the steady state has been achieved. Okay. So the algebraic unknown roots S1, S2 can be found where the steady state response is given by the particular integral part of the solution, which depends on the type of the input that is applied. Okay. Then method of D operator, it says that D operator or Laplace transform can give solution to the linear higher order differential equations. Then the particular use of this is in terms of the digital simulation. If the real-time response of the measurement system is to be taken into account for process control, so we go for this digital simulation where the complex equations are possible to be solved, which are going to consider the even time varying signals, the output given for those kind of signal, even with non-linear kind of the inputs. Okay, so this is nothing but the transfer function. Say this is what I called in earlier diagram as a measurement system, a block diagram for measurement system, where there is some input is given and we are going to find out the output of the measurement device. So this is going to be the transfer function, the representation, the functional relationship between input or output. We call that as a transfer function. So it gives it predicts the general relationship between input and output characteristics. Okay, so it is not an instantaneous ratio, but it is a time dependent response. So it is represent to easier to give in the form of block diagram graphically. Okay, so it gives the overall characteristics of system or the components of the known characteristics. Now let us say that into your measurement system there are number of elements. So for example, physical element called as a transducer, the element called as amplifier, and the recorder. Suppose there are three physical devices which are going to make the complete measurement system. So this is my measurement system and having three different component 1, 2 and 3. So transfer function of each, because of the input given by the system 1 first. So if I consider this as a very first stage, the transfer function can be given in some mathematical formulation. So input given to the transducer and output given by the transducer will be related by means of this transfer function. Coming to the next one, say amplifier is the second stage. Input is given to the amplifier and it is going to represent the signals at the end because of the mathematical relationship between the input and output into the amplifier. So this is going to display or give some kind of signal here, which are functional to the input depending on the type of the transducer being used, say amplifier here, and third one is amplifier, the recorder. So the input given to the third one, recorder, will be say in the form of signals, say, and the total output of the system QO will be a combined function of the relationship between input output for element 1, element 2 and element 3 as a combination. So the total transfer function of this measurement system will be represented something like this, where there will be say very clear input and the output given by the measurement device. So this is nothing but a combination. It's a straightway kind of multiplication between the transfer function of phase 1, 2 and 3. And under such condition, then we apply the standard input at the very first stage, and then we find the response at the end. We find out how the dynamic characteristics are given by the instrument. So this is called as a combination of the individual transfer function, and this is only say workable or is going to represent faithfully the transfer function of the system if there is no loading or negligible loading. I think this we have discussed number of times. If there is no change in the input quantity because of the loading effect, then only you can understand that the signals are fairly representing the true input. If there is larger loading, the true input will not be taken to the say very initial stage of the measurement device. Right? So we'll see. Say similar thing can be done with the help of Laplace transform. It is commonly used for the linear system. Transfer function is nothing but the Laplace transform of the output quantity to the Laplace transform of the input quantity. All initial conditions are at 0. Then transfer function is found out. I think you are aware of this one, how to use the Laplace transform. So D will be replaced by S. So wherever we use the earlier equation, the D operator, that will be replaced by S, so that you can use the Laplace transform for getting the mathematical modeling of the instrument. Right. So I think we'll be able to restrict our discussion for the dynamic characteristics here. I don't know how much time we left with. So I think we'll be able to start with the zero order system. I'll share the other transparency. Let me know any difficulty in understanding what is the standard method for solving to get the dynamic characteristics of the system. So thumb rule is there. We are going to represent mathematically the system. Then we are going to apply the standard input and finding out the response of the system. If the response is not as per the desired condition, we are going to apply some kind of compensation. And for that, we are going to form the linear equation. Let us consider now zero and the first order system. Based on the mathematical model, we are going to classify those in the zero order system and the first order system. I think this is very simple to understand. So for zero order system, all coefficient other than the constant AO and BO are 0 in the generalized model. And thus these kind of systems are called as the zero order systems. Say for example, on applying the condition that the other constants are 0, say AO and BO, other than AO and BO, the two constants or everything else is 0. We call that as zero order. So in this condition, AO times QO, sorry, A0 times QO is equal to B 0 times QO. I think there is some mistake. It should be the here as input. Please make the proper corrections. So in this one, we can have the value of the output given by the system is nothing but BO upon AO times QI, and thus this function of constants will be called as a constant K, that is nothing but the sensitivity of the instrument or the measurement device. let us understand this again. So the K that we have found out in case of the simple relationship between input and the output of the measurement system, we found that is going to be a linear one. So this is what is represented in the form of K, which is nothing but the some value BO upon say AO, sorry, B0 upon A0. So this is a very simple system wherein the dynamic characteristics are more or less representing the similar pattern or the same way as that of the static measurements. So basically we call these as nothing but the simple instruments wherein there is no effect of the time variation of the signals. So that it will always give dynamic response which is very ideal and very perfect. It is as good as very close to the static characteristics of the system. Here it will be ideal because the instance input is applied is going to represent some output. So time lag, response time, these entities will come down to standstill condition. So it is as good as the static response. That is why it is called as an ideal or perfect dynamic response of the zero order system when applied with some standard input. So irrespective of the nature of the input, maybe say with some intensity variation or some kind of the angular speed, output follows very faithfully or very truly to the given input. So if we have talked about the fidelity as a very important dynamic characteristic, in this case it will be a accurate system having 100% fidelity. It will be very closely or exactly matching with the input, though we will have a small delay or will have a small bias, right? And the signals will not distort. There is no distortion of the signal. The signal pattern, suppose I am showing here as an input signal given with some different colors, a blue color, you will find the same nature is there for the output. There is no distortion. Now, what is the distortion? If the signals are moving with some different pattern than the standard input, say with red color, if I am showing the standard input, the output will be shown in blue color. Then we say the signals are distorted. There is a major distortion because of waviness and so on. It's not going to happen in case of zero order system. These are the say physical realities of the zero order system. If we compare with the non-zero order systems. So there is no distortion, there is no time lag. Faithfully, the input is represented in the form of output. There will be little delay, little bias, which already we have quantified in terms of the static characteristics of the system. Then there will be no lag. So I think the important properties we see, there will be no dynamic error. There will be no fidelity. Fidelity will be say very optimized, 100% fidelity. There is no delay, there is no time lag, there is no phase difference, there is no distortion. And that is why we call this as the ideal or the perfect dynamic response if the zero order system is there. Right. So let us consider a potentiometer. It's a very good example of a zero order system. The potentiometer is going to give the change in the resistance with respect to the slider displacement, a linear displacement or angular displacement of the slider. I think this we have seen in case of our one of the experiment where we have seen the angular displacement measurement. The other experiment we have seen the linear displacement measurement. If you recall, there was one potentiometer and having the probe. This probe is moving against the scale of 0 to say 5 centimeters. Here it is moving from 0 to 300 degrees. In our experiment, I think you can recall. So this potentiometer is a very good example of the first order instrument because the response of the system is linear and the constants other than A0, B0 are going to remain. So they are not going to play a role into the particular mathematical formulation. So the equation for this will be very simple. QO will be BO by AO times QI, which is nothing but K times QI. In this condition, say if Xi is the displacement given and L is the total length, say total length of the potentiometer resistance, the total length in which the slider is going to move over, and xi is any instant the given slider touches the resistance, say this is xi, then you can see that the output EMF or output voltage generated will be equivalent to xi times L times xi over L times the applied voltage, which is nothing but k times xi. So see here the example, that is what I have shown here. See, EB is the EMF applied over the length L of the resistance wire, and this is the position of the slider, instantaneous position of slider, say at xi from the reference point. The output EMF will be proportional to the constant, that is xi times the total length, or xi over the total length. So if I take this at any instance of position, if I know the value of k, the output can be found out. Say output EMF will be equals to, sorry, the input EMF generated EO will be equals to the proportion of k times the value of xi. No, sorry, it should be k times xi into EB. Something is left over here. K times EB, not xi, because xi we already considered here, right? I will make the corrections. So please consider this as k times EB, not xi. So this is what is required. Now, the potentiometer, see the input that I am going to apply. The input is applied, say for example, the displacement is given and input is applied here. The output is something, say k times Q instantaneous input that has been given, KQIS. Then the frequency response, there is no change in the frequency. So frequency response also will be more or less same as that of the input applied. Though there is little variation, but the output will be corresponding to the given input. So if xi is the displacement, if I approximate this to a line, the EO will be more or less proportional to the displacement. In actual fact, this is the actual curve. Because of the, say, resistance of the wire itself, there is some change into the input signal, but I can approximate that to the straight line, which is very closely representing the input in terms of xi, that is with respect to time varying. Right. So ideal zero order instrument, I think, shall I stop here? I will stop here. Right. So we'll discuss from this in the next class. Okay. So mostly I'll declare the portion also in the tomorrow's class, portion for your sessional examination or mid-sem examination. Now I would like to iterate again. This is a very simple part to understand. You might have gone through many of the terms somewhere else. Right. You please refer the textbooks. Most of the material that I have taken from the book of Dublin. You may see that. If there is doubt, you can let me know. Okay. Thank you for joining.